Good day, everybody. Today we're going to talk about Lesson 1-2, Relations and Functions. Functions are the mathematical models of relationships between two variables. And you're going to hear me say this a lot, so you're going to want to write this down. To know that it is a function, you have a function when every x value aligns to exactly one y value. Okay? We'll get more into detail here in just a little bit. If you look at slide 2, you saw a graph of the yearly closing prices of gold at the beginning of this chapter. It's located right here on the screen. The closing prices for 1966 to 1975 are given in the following table. So, here's my year, 1966, 1967, all the way down to 1975, okay? So they call this year Y. My closing price is P in dollars, so $35.40, $35.50, sorry. 1971, $43.80, okay? As you can see, the price of gold went up all the way until 1974 to where gold went back down again, okay? Now, this is a relation, okay? You have a set of x coordinates, you have a set of y coordinates, or we could call these our x coordinates, or we can call these our y coordinates. It shows you on the next slide how you can graph those either way. Okay? Two graphs of these data are shown. Notice, they have the years here in the x values. They have the closing price in your y values. It's important that you know that these are x values going across here. These are y values. Yes, I know it's kind of tricky because they're using this as a y here, but that y is standard for year, okay? Don't let the book mess you up, okay? This is still the x-axis. So, over here, they plotted closing price to year. Notice how I said that. Closing price to year. Okay, so all they did was the closing price is now their x values of their gold, and their year are now their y values. Now, to me, I would always put years down here at the bottom, but that's just me. Sometimes people do things a little bit different, and you have to be able to read graphs to understand what they are trying to tell you. Okay, you should note that both these say the same thing. Okay, in 1969, we can see that gold was roughly, well, it says in between 25 and 50, so about 30-some, maybe $33, something like that. Same thing over here. We can come up here and see that in 1969, it's still right around that $33, $35 mark. Okay? Moving along. Each of these sets of ordered pairs in their graphs show the relationship between the variables y and p. In general, a relation, and this is important for you to know, a relation is any set of ordered pairs. So any set that you can think of is a relation. Everything is a relation. It depends on certain stuff if it is a function or not. Okay, and we're going to get into that in just a little bit. It says any correspondence of pairing between two variables can be written as a set of ordered pairs. In the relation of y comma p is this graph right back here, y comma p, because my years are first, my closing price is on my y-axis, so this is y comma p. This over here would be p comma y, because we did our closing price here first, our year second. Okay. Graphed on the left, no two ordered pairs have the same first coordinate. Okay. So if you go back here, none of these have the same first coordinate, correct? It goes from 66 to 67, 68. Never have duplicate years. Okay. Each value of y relates to one and only one value of p. If you have a relation that maps to one and only one value, then what you have is a function. Okay? If you have a set of x values that only map to one number, okay? And if all these are different, they definitely map to one number. What you have is a function. And here's your definition for a function. A function is a set of ordered pairs, x comma y, in which the first component x of a pair is paired with exactly one second component y. So what you're checking is that every single x value goes to exactly one y value. And we're going to have some examples here in a little bit that's going to show you that. Continuing on. In the relation y comma p, that's where our years were first, our cost was second, the variable p is the dependent variable, okay? Is the dependent variable. So the second number in your ordered pair, normally your y values, are what we call dependent variables. Why are they dependent? It's because they're dependent on whatever the x value is. Okay? In this case, p is dependent on y. Okay? We call y, or the x-coordinate, the independent variable. Okay? The independent variable is able to stand alone. It's able to do stuff by itself. You will not know the value of p unless you know the independent variable. Okay? Sometimes the independent variable values of a function are called inputs. You heard me say that in Algebra 1. Okay? Sometimes we call our x-coordinates inputs. This would be an input. That means my y-coordinate would be called the outputs. Yes, dependent variables are called the outputs. You put something in to get something out. Okay? You put something in to get something out. When a relationship between two quantities is a function, we say that the dependent variable, notice this wording, okay, because this is where a lot of people get mixed up. Watch this wording. We say that the dependent variable, that's the second component, is a function of the independent variable. So up here, we would say that p is a function of y. You say the dependent variable first, okay? you say the independent variable second. P is a function of y, so you got to watch how that's worded. We also like to say that the function maps each value of the independent variable onto the corresponding value of the dependent variable. So what you can also say is that y maps onto P. Y maps onto P. Okay? And it's all about the wording down here. And here's another definition of a function that they just reworded for you. It says, a function is a relation in which no two ordered pairs have the same first component. So what that means is, when you're looking through your ordered pairs, there cannot be a relation that has two x values that are the same. And like I said, we're going to get more into that in just a second. Not every relation is a function. Remember, everything's a relation, but it doesn't always have to be a function. It says consider the relation with the ordered pairs P comma Y. So this is where our cost was first, our years were second. Both 35.4 comma 1966 and 35.4 and 1969 are in this relation. Well, notice, both their x values are the same. Since their x values are the same and their y values are different, meaning we have different y coordinates, this number doesn't map to exactly 1 year. It maps to two different years. It maps to 1966, and it also maps to 1969. So, P comma Y's information is only a relation. Okay? Is only a relation. Y is not a function of P, so that's how you would say that. Y, remember dependent variable first, is not a function of P. You have to have that not in there because it maps to two different y values. The table and list of ordered pairs in the situation about gold prices are examples of mathematical models. You're going to see a bunch of mathematical models from here on out of yearly gold prices. A mathematical model for a real situation is a description of that situation using language and concepts of mathematics. So sometimes you're going to have to decipher in these mathematical models and determine what is going on in them. Let's get into our examples. Example 1 says, in a triangle, the sum of the measures of the two acute angles is 90 degrees. We should all know that. Okay? That's a 90 degree. The rest of the triangle has to be 180. So these two angles have to add up to be 90 degrees. That's this equation right here. Suppose x is the degree measure of one acute angle and y is the degree measure of the other. They're both acute because they have to be under 90. You can write an algebraic sentence to describe the situation. They got x plus y equals 90. X plus y has to equal 90. Now you can subtract x from both sides of the equation to get y alone on one side. So that's what they did. They subtract x. Okay? The question is in example 1. In this question, which of x or y is the dependent variable? And which is the independent variable? Go ahead and pause and answer this for yourself. Which is the dependent variable? Our dependent variable is whatever is dependent on the other. Y is the dependent variable. Why is y the dependent variable? Because we don't know y unless we know x. Okay? So y is dependent on x. That makes x the independent variable. So if I told you x was 70, independent variable, stands alone, you can now tell me that y is 20, because both these have to add up to 90. Okay? Example 2. Here's a relation that I was talking about. Here's a relation. We have years and we have percents. Here are ordered pairs. Okay? You can go either way. You can go 1986 to 19, or you can go 19 to 1986. Okay? This is just a relation. It's just written in a table form a different way. It says the percentage P of the adult U.S. population aged 25 and over who had earned a 4-year college degree by year Y is given in this table. Okay? A says, is Y a function of P? Now remember how I told you to watch for the wording. This is my dependent variable, so this is my x. This is my independent variable. Sorry, yes. This is my independent variable, x, sorry. This is my dependent variable, which is my y, sorry. Independent variable, dependent variable. Dependent variables are written first, okay? So, I'm looking at my x values. My x values are my p's. My p's are on the bottom here. Okay? As I look through these p's, okay? As I look through these p's, are there any p's that are the same? Well, you're saying 28 and 28 are the same. 21 and 21 are the same. Do they map to the same thing? Well, it says this 21 maps to 1990. This 21 maps to 1992. 28 says it maps to 2004, and it also maps to 2006. So, is y a function of P? You are going to say no. Why? Because 21 and 28 map to two different coordinates. Okay? So let's look at B. Is P a function of y? So now in this case, y is our x values. P is our y values. Okay? Y is our x values. P is our y values. Y is our x values. P is our y values. Okay? Now, y is my x coordinates. So if you look at y, are all the years different? 86, 88, 90, 92, 94, 96, 98, 2000, 2002, 2004, 2006. Are they all different? Yes. Since they are all different, we know, yes, P is a function of y. All independent variables are different. This is all I have for you today. I hope it all makes sense. We'll see you tomorrow.